Okay, in this video I'm moving on to Chapter 6 of the Cisco ONS 15454 DWDM system guide. And in Chapter 16 we talk about multiplexer, optical multiplexer and demultiplexer cards. So you'll recall that we gave a block diagram of the WDM system. Let's see if I can dig that out for you here. Okay, here was the very basic block diagram of the DWDM system where we had optical multiplexers and demultiplexers. So this was the MUX and this was the DMUX. Multiplexer, demultiplexer. Here we're combining many into one, and here the DMUX we take many and we separate. We take one fiber with all the signals and separate them out into many fibers. Okay, so okay. Well, in Chapter 6 we have three different cards, three different card types described: the 32 MUX and the 32 DMUX, and the 4MD XX.X. The MUX is it has 5 sets of ports on the faceplate. It operates in slots 1 to 5 and 12 to 16. DMUX also has 5 sets of ports. And then the 4MD has 5 sets of ports also. Let's go see how all this works. All of these cards have been around since the beginning, and they're all compatible with all the software versions. Okay, and let's look at the 32 MUX card. Okay, so the 32 MUX card is a 32 channel multiplexer card that multiplexes 32 100 gigahertz space channels of this channel plan. It takes up to 2 slots in the 454, so it's a wide card. And so if you look at the transport platform, you can see the optical multiplexers and demultiplexers are these big wide ones with 5 optical ports on them. Okay, they're the MUX and DMUX. Okay, so the functionality. It has an arrayed waveguide grading device, an AWG. This is where a lot of my deep understanding is in terms of operation, the physics, and the details of fabrication of AWGs on silicon platform. I spent some years of my life working on these. Our biggest customer was Lucent. We sold a lot of AWGs to Lucent for their earlier generation DWDM system, and I was product line manager and lead engineer on those devices at JDS Uniphase. Okay, each single channel port is equipped with a variable optical attenuator, a VOA, for automatic power regulation. And each channel is also monitored for automatic power regulation. Okay, what do these cards look like? Well, they're actually very simple. Here's the block diagram that shows both electrical and optical parts to it. We have to have a processor, a power supply, and an FPGA. And in fact, AWGs are temperature controlled devices. So here's the optical module, and you can see it really does have 5, well, it's supposed to have just 5 ports. 1, 2, 3, 4, and then 5, the transmitter. The monitor port, I don't know, is that, can you see that on these cards? I don't know. Where's the monitor port? These are the MUX and the DMUX. Maybe this thing up here at the top is the monitor port? Or this one at the bottom? I don't know. In any case, the main 5 are 4 inputs for 32 channels, and each of these is an 8-channel ribbon fiber. Okay, I think I talked about ribbon fibers at one point. And here's what the optical block diagram looks like. It's very simple. It is an optical multiplexer with 32 inputs, 8 fibers at a time on those inputs, and those are special connectors. They're called MPO connectors. They contain 8 fibers, so they're called a multi-fiber push-on cable on its front ply. And the MPO cables break out into 8 separate fibers, okay? And each channel has a VOA, these variable optical attenuators, and each channel has a photodiode for monitoring purposes, okay? And so this is exactly the type of thing we used to make for Lucent. We actually made them in the early days before we had VOAs and photodiodes on every channel, but we were working on developing those things. And the guys who I used to work with still work at JDS Uniphase, and they're one of the principal suppliers to the world of AWGs, still making these guys. Okay, so that's the multiplexer. The demultiplexer is really just basically the same thing in reverse. Again, 4 inputs with 8 fibers each, and then a single fiber on the output. And again, we have VOAs and photodiodes on every channel. So we can monitor the power with the photodiode and then feedback to adjust the power with the VOA. And what we want is we want all of these channels to have the same power, okay, in a DWDM system. And as I mentioned before, sometimes you have all of your channels turned up, but usually you only have some fraction of them turned up. And the more channels you turn up, the less power there is for each channel. So you definitely want to have all of this functionality in the MUX and DMUX units. One thing that you may not appreciate is the AWG design is actually very different for the MUX and for the DMUX. For the multiplexer design, let me draw a picture for you. For the multiplexer design, it's very important that we have very flat. Okay, so for the MUX, we have this device. We have many inputs and only one output. And for the MUX device, what we want is we want to have, as a function of wavelength, we want to have the various channels. Each channel is a bandpass filter, essentially. So we want those channels to be very flat at the top, and this is on a decibel scale for what they look like. We want them to be flat at the top, and we're not so worried about whether or not there's a lot of crosstalk from one channel to the other. So for example, this channel, by the time you get to the center of this adjacent channel, this one doesn't have to be so far down, okay? And that's the reason is because only one wavelength is coming in on each channel, okay? So we don't worry so much about crosstalk between the channels as far as these multiple bandpass filters. But what we do worry about is the fact that they're flat at the top, and that's because these lasers, their wavelength may drift slightly. And if their wavelength drifts, we don't want the power to vary as the wavelength drifts. Okay? So that's how you design a MUX. For a DMUX, what you're doing is you have many channels coming in, and they're all coming in at once. Okay? And that, for that reason, you need to have these bandpass filters need to be very well separated. And they don't need to be flat. They don't need to be nearly as flat at the top, but they need to have very low crosstalk. So if I take the center channel of this channel and I go to the adjacent channel, its crosstalk value better be very low. Okay? So crosstalk is not a problem. And we want a flat top. Here we don't care about a flat top. We can use a Gaussian, and crosstalk is a big issue. Okay, so that's the difference between the MUX and the DMUX. Finally, just to wrap this chapter 6 up, we have what are called the 32DMXO cards. These are oh, they're the ones I just talked about. They're the DMUX cards. here's the one I wanted us to talk about. We have the 4MD XX.X cards. Okay, there's a whole bunch of these. These are 4-channel add-drop or multiplexer demultiplexer cards. So we have 4 100 gigahertz space channels, and we can drop, and we can multiplex or demultiplex just 4 of them at a time. So here's the optical or the block diagram. So this optical module now contains a MUX and a DMUX. Has channel outs, channel ins, okay, and here's the block diagram on the optical side. And so it shows a MUX and a DMUX both in the same package. Okay, it's only 4 channels. Each one has a photodiode monitor and a VOA on it on the MUX side. The DMUX side, you don't need the VOAs. You want all the power you can get to go to your transmitters. Here on the DMUX, we did have VOAs, huh? Well, in general, you're going to take all the power you can get, send it to your photodiodes for in a DMUX functionality. In any case, it's only doing 4 channels at a time, but this is a 100 gigahertz channel spacing channel plan, right? 100 gigahertz space channels. Well, okay, so first of all, you can specify which set of 4 channels you want by the XX.X. If you go 30.3, you're going to drop these 3 channels: 30.3, 31.2, 31.9, and 32.6. So you can specify any one of these 8 different varieties of this device. Okay, and here's the channel plan. I guess I should have shown you a channel plan up by now. In any case, in this channel plan, we have channel numbers 1 through 40, and the channel ID is based off of the wavelength numbering, but you'll notice that it's the frequency which takes even steps. So this is a step of plus 100 gigahertz, which is 1/10 of it. This is mislabeled. This is supposed to be terahertz. This is 195.9 terahertz and not 195.8. And if you add 100 gigahertz, which is 1/10 of a terahertz, you'll go from 195.8 up to 195.9. Okay, so you can see that we have even spacing exactly on the numbers on the frequency. But based on the crazy number that is the speed of light, you'll get all these crazy different wavelengths. The other thing is you'll get a wavelength spacing which is non-uniform across the band. Okay, and so as you go from channel 1 at 195.9 and you take up 40 steps up to the top channel, oops, I don't have the rest of the page, I only go down to 30, you're going to go from 1530 all the way up to, I guess they showed us here, 1530 up to 1566, I guess it was. Well, wherever we just read that. In any case, the 100 gigahertz spacing translates to an approximately 0.8 nanometers as a delta lambda. So this is our delta F, and this is our delta lambda. If we go to 50 gigahertz channel spacing, then we're going to get a 0.4 nanometer delta lambda. And the 100 gigahertz gives us 40 channels in the C band, and the 50 gigahertz is going to give us 80 channels in the C band. Okay, and so these are these wavelength ranges. So you got 40 channels, you got 4 channels per device, and that means there's 8 different flavors of the device. Okay, and I think that's it for Chapter 6. Next we'll talk about Chapter 7. Thank you.